Did you ever want to learn about OOP? Well, now's your chance because you're watching Learn with 2C. Hello, everyone, and welcome to another episode. For today's topic, we're diving into object oriented programming, or OOP. But first, let's ask ourselves what exactly is OOP, and why is it important to us as programmers? OOP is a programming approach that organizes code into objects, each representing a real-world thing, like a person, an animal, or even a villager. Each object has its own attributes, or data, and behaviors/actions. It helps make code easier to manage, reuse, and understand, especially in big programs. To make this easier to understand, we've built two micro-villages to show how programming styles differ. One follows procedural programming, and the other follows object-oriented programming. Village 1 has Chief Dherae, while Village 2 is led by Chief Gian. Let's see how they each run their village. Here we are in the procedural village, where Chief Dherae runs everything the traditional way.
Here, one villager does everything. No classes, no objects, just one nitwit with a long list of chores.
6.5 hours later.
And that's procedural programming. One sequence of instructions done step by step. It works, but it's tiring, repetitive, and hard to manage as the village or the code gets bigger.
He did everything, but it took forever. No.
In code, that should look something like this. In this program, every task is written as a separate function and executed one after another inside the main method. The code runs in a fixed sequence, step by step, from top to bottom. The problem with this approach is that as the program grows, it becomes harder to maintain. Each time we add a new task, we need to write another function and update the main method. There's also no clear structure to group related data and behaviors together, which makes it difficult to organize or reuse code. If two functions share the similar logic, we'd have to rewrite the same code instead of just reusing it. That's why procedural programming doesn't scale well. It works fine for small programs, but as complexity increases, with more tasks or entities, the code quickly becomes long, repetitive, and hard to modify. Let's see if Village 2 does it any better. We're now here at the OOP village, run by Chief Gian, who believes in teamwork and structure.
Here, no one villager does it all. I started with a basic blueprint, a villager class, and from it, I created specialized villagers, farmers, armorers, librarians, butcher, and toolsmith.
A few inches later.
Whew! We finish all the work even before the day ends. That's the power of OOP, guys, where everyone have a clear role and are organized.
And that's OOP. We divide responsibilities between objects instead of one long list of steps. And in programming, it should look like this. Here, The distribution of jobs to different villagers uses the inheritance method, containing a superclass and multiple subclasses. But we'll discuss that surely later on. For now, let's focus on understanding the object-oriented programming approach itself. In this program, we can see multiple classes that make up the structure of our code. Each class is a blueprint that defines a specific attributes, behaviors, and in some cases, a constructor, which is a special type of method used to initialize objects when they are created. In our villager class, the attributes include variables like name, experience, and how many emeralds they have. These describe the data that every villager object will have. The method, the method it defines the behavior, something that every villager can do. We also have a constructor which sets initial values for each object's variables. The constructor in this example is a default constructor, one that exists even if we don't explicitly write it. By declaring it manually, we can set initial values such as 0 or null. Later, if we want each object to start with custom values, we can use parameterized constructor, which allows us to pass data when creating the object. Now, let's move on to the main class. This is where we create and use our objects. To instantiate a class, we write the class name, followed by an object name, an equal sign, the new keyword, and then the constructor call. For example, villager v equals new villager. This line creates a new villager object and stores it inside the variable v. Once an object is created, we can access its variables and methods using the dot notation. That means typing the object's name followed by a dot, then the variable or method we want to use. So when we write farmer.plantcrops or armorer.eat, we're instructing that a specific object to perform the behavior defined in its class. The OOP approach separates code into modular components, each representing a specific role. Instead of one long block of procedures, we now have multiple smaller self-contained classes that work together to form a complete program. This design makes the program easier to maintain, expand, and reuse. For example, if we want to add another villager type like a cartographer or a cleric, we can simply create a new class that defines their unique task without changing any existing code. Now, we can see that each object has its own role. The farmer harvests, the librarian trades, the armorer crafts, and so on. Each one performs unique tasks defined in their own classes, while still sharing the same basic behaviors from the superclass of the villager superclass. This shows how object-oriented programming allows us to divide work efficiently between multiple objects, keeping our code organized, reusable, and scalable. Now, let's take a closer look at the concepts behind this. Now, first, we have our classes and objects. These are the foundation of object-oriented programming. A class is like a blueprint or template. It defines what an object will look like, its attribute, and its behaviors. Attributes represent data or characteristics, while behaviors represent the actions it can perform. In our example, the villager class contains attributes such as name, XP, and emeralds that they have, which describes a villager's identity and progress. It also has a method called eat, which represents something every villager can do. Here, both V1 and V2 are objects created from the same villager class. They share the same structure, meaning they both have a name, experience points, and emeralds, but each hold its own set of values. When we call v1.eat and v2.eat, each object performs the same actions, but with its own data. Steve is eating and Alex is eating. Same behavior, different objects, different data. This shows how objects bring classes to life, turning a single blueprint into multiple unique instances that can interact and perform tasks independently. In short, a class defines what something is, and an object represents a specific example of it. This is what gives OOP its flexibility, allowing us to model real-world entities inside our code. Next, we have inheritance. Inheritance lets one class reuse the traits and actions of another class. It establishes is a relationship between classes, where one class, the subclass or child class, inherits properties and methods from another class, the superclass or some call parent class. In our example, the villager class acts as the superclass. It defines the shared attributes and methods like name, XP, emeralds, and the eat method. Then we have multiple subclasses such as farmer, librarian, armor, butcher, and toolsmith, each extending the villager class. By using the keyword extends, these subclasses automatically inherit everything from the villager class, meaning they will all have access to the same attributes and behaviors without needing to rewrite them. As you can see, the farmer object can still access the eat method even though it's defined in a different class. That's because the farmer class inherits everything from the villager class through the extends keyword. However, when we try to make a V1 object which belongs to the villager class, called the plant crops method, it results in a compilation error. That's because plant crops exists only in the farmer subclass and it's not part of the villager class. The main purpose of inheritance is to promote code reusability and hierarchical organization. Instead of writing the same attributes and methods repeatedly across the multiple classes, we can define them once in a superclass and let the subclasses inherit them. This approach not only makes the code shorter, but also ensures consistency. If we ever need to change a common behavior like how villagers eat, or we can just modify the method in the superclass, and all the subclasses will automatically reflect that change. In real-world programming, inheritance is what allows developers to build complex systems from simpler, reusable components, just like how our specialized villagers share the same foundation but perform their own unique roles. We've now seen both sides of programming, the step-by-step approach of procedural programming and the structured reusable design of object-oriented programming. In procedural code, every task is handled one by one, which works fine for small programs but quickly becomes difficult to maintain as complexity grows. Object-oriented programming solves this problem by organizing code into classes and objects, separating responsibilities, and promoting code reusability. By using principles like classes, objects, and inheritance, OOP allows developers to write cleaner, more scalable, and easier to understand code, much like how well-managed the village runs efficiently when everyone knows their role. In the end, both styles aim to get the job done, but OOP stands out for making complex systems manageable. It's not just about writing code, it's about designing smarter solutions. And that's how object-oriented programming changed how we build and create software. One class, one object, and one idea at a time. This has been Learn with 2C. Thanks for watching.